how do we calculate forces in the members of a truss. We are going to restrict ourselves to plain trusses, which are the ones that I showed you, and we are going to do our analysis under certain assumptions. Number 1, when these members, which we take to be sort of rods, but are wide enough, when the middle line, wherever it cuts, we are going to take that intersection as a pin joint. So, intersection of the middle line of members of a truss are taken as pin joints, and as a corollary, we are also any plate or bolting that can be done here, we ignore the torques arising because of that. Next, we are going to assume that at any truss, all the load is going to be only on the pin joints. That is the next assumption. And finally, if members, that is these rods, have weight, the weight is equally distributed on the pin joints. That is, if for example, a member may have a weight W, then I am going to say that this pin joint bears W by 2 and this pin joint also bears W by 2 of this weight. So, the weight is equally distributed on the pin joints. Under these assumptions, we analyze the trusses. There are two methods of analyzing the trusses and getting the forces on various members. One is known as the method of joints, and the other one is known as the method of sections. You have already seen, already gotten a glimpse of method of joints when I analyzed a very simple truss earlier. What is done in method of joints is that each point, each joint of the truss is brought in equilibrium under the applied forces. So, if I have a truss like this, and it is loaded here, then we start with a point where the load is and see how that point is in equilibrium. That gives us the forces in the various members that are connected with that point in terms of the applied load. In case you have more forces than you can solve for in this case, then you first solve for the reactions at the fixed points, and then because there are only two members at those fixed points, you can solve for the forces in those members and then go on to the next joint and so on. I am going to demonstrate the method of joints through several examples. As the first example, let me take a system, a simple system which is made of 4 rods with one fixed pin joint here. This is a rod, another rod like this, the pin joint here, third rod like this, and this is on a roller, a fourth rod like this, and there are two ropes along the diagonal. Let me call this system A, B, C and D. This length is 4D, this length is 3D, and we load the system once at point B by a load L, and another loading is done at point C, the same L. These are two ropes, A, B, C and D, and in both the cases I want to know the forces developed in these rods or members and these ropes. I should also mention here that this problem is taken from the book of Merriam. This is quite a nice problem because it teaches us quite a lot of things in one problem. So, let us first take this particular case where we have, I will just make it a very simple manner, these points. This is on a roller, this is on a fixed pin, this is a rope, this is a rope, this is the load. This is 4D, this is 3D. Now, on the point, this is A, B, C, D. On point D, there will be only a reaction in the horizontal direction. Let me call it ND on the entire system. So, ND in horizontal direction. On point A, there is going to be a reaction in the vertical direction. Let us call it N Y, N A Y, and horizontal direction N A X. This is if I consider the entire system as a whole. So, on the entire system, if I make a free body diagram, there is a load L, there is a reaction here N D, there is a reaction here in the vertical direction N A Y, and there is a reaction here in the horizontal direction N A X. Since there are only three external forces N D, N A X and N A Y, these can be determined very easily. It is a two-dimensional problem. So, let me make it again. There is a load L, N D, N A X, N A Y, summation f x equals 0 gives N A X plus N D equals 0, and summation f y equals 0 gives N A Y equals minus L. Oh, sorry, I should write N A Y minus L equals 0 or N A Y equals L, that is, it is vertically upward direction. Summation torque about D, this is point D, A, B, C, is equal to 0 gives 4 D times L clockwise plus 3 D times N A X also clockwise should be 0, and this implies that N A X equals minus 4/3 L, and minus sign tells you that its direction, let me make the good direction with red, should be this way. So, this is NAX. And from this equation that NAX plus ND equals 0, ND also comes out to be in the right direction 4/3 L. So, now we know the forces, external forces in the system. What we have is L here at point C, point A, I have a force acting towards the left 4L by 3, force acting towards vertically up L. I have a force acting on this joint in this direction 4L by 3, and I want to calculate other forces. This is point C, this is point D. Let us take the joint D or pin at D and see what the forces on D are. Now, we are really using method of joints. Each joint we are going to bring into equilibrium by applied forces. At point D, there is a force in horizontal direction 4 L by 3. There is a force, and now I am anticipating that the force by rod DC is going to be towards the left F DC. There is a force by the rope. Now, since this is a rope, it can apply only a tensile force. I mean, the rope can exist only under tension, not under compression. So, it will not support a compressive force. So, it can apply only a force in this direction F, let us call it dB, and there is a vertical force due to rod FAD. Now, one can see that this joint is under a force 4L by 3. So, this is going to be pushed to the right, and if it is going to be pushed to the right, the rope is also going to be pushed in, but rope cannot sustain any compressive force. So, F dB is going to be 0. If F dB is going to be 0, that means there is going to be no vertical component of force due to element dB. This also implies that FAD is equal to 0. So, we have found two forces, FDB, which is 0, and FAD, which is 0. Let us now consider the forces in the horizontal direction. Since FDB is 0, summation Fx equals 0 gives me FDC equals 4L by 3, and positive sign tells me that I have found the correct direction. Since the rod DC is pushing the point out, the rod DC is under compressive forces. So, this is compressive. Let us move on. So, what we have found in this that at point D there is a force 4 L by 3 and A, B, C, D. F A D is 0, F D B is 0, F D C is compressive 4 L by 3. Let us now look at point C. Point C is under a force F D C, which is 4 L by 3. There is a force, and I am already anticipating the right direction, F A C, pulling it in. That means AC rope is under tension, and remember again, AC is a rope, so that it can support only tension, no compressive force, and there is going to be a force F BC. This angle is, let us say, theta, this is theta. So that, let me write in different color, cosine of theta is 4/5 and sine of theta is 3/5. So, summation Fx equal to 0 on point C gives me FAC cosine of theta equals 4L by 3. So, FAC is equal to 4L by 3 divided by cosine theta. So, that is 5/4, and this gives me 5/3L. That is the tension tensile force on the rope. Now, similarly, if I do summation Fy, so again let me make the picture. A, B, C, D, we have found FAC to be 5/3 the load. This is the load. At point C, this is 5/3 the load, this is 4/3 the load, and this force is FBC. Summation Fy equal to 0 gives me FBC equals 5/3 L times sine of theta. Sine of theta we have already calculated is 3/5, and therefore, this comes out to be L. So, FBC is pushing it down, and that means FBC is, the rod is being compressed, so it is compressive. So, we have found force FDC, we found force FBC, we have found force FAC, we have found force FAD, we have found force on FBD. The remaining forces are forces only on FAB. Let us now look at point B. The joint B is under load L, then it is being pushed by FBC by L. There is no force, 0 force due to the rope, and therefore, FAB comes out to be 0. Cut. This follows from the condition summation Fx equals 0 on B. So, now we have found all forces, and let us see again by checking at point A whether all the forces are consistent. So, what we have found on this frame, A, B, C, D, F, A, B is 0, F, A, C is 5/3 L, F, D, C is 4/3 L, F, B, C is equal to L, F, A, D is equal to 0, and F, D, B is equal to 0. With these forces, let us see if point A is under equilibrium. Remember, we found that on A there is a force in this direction which is 4/3 L, there is a force upwards which is L, and now I know, because of the tension in the rope, there is a force F A C which is 5/3 L. This angle is theta. Recall again that cosine of theta is 4/5 and sine of theta is 3/5. If everything has been solved correctly, point A again should be in equilibrium. So, f AC cosine of theta comes out to be 4/5 times 5/3 L, which is 4/3 L, and this force is going to balance this force out. So, horizontal forces are 0 and F AC sin theta comes out to be 3/5 times 5/3 L, which is L, and this force is going to balance out this particular force, and therefore, point A is in equilibrium and we have solved the problem correctly. For the second part, where the system is loaded differently, that is, the load is at point C. I will leave this for you to work out. In the next lecture, we will be taking slightly more complicated and bigger examples and see how method of joints helps us in solving the problems for trusses.